Today's lesson is going to be on special right triangles. And there are two types of right triangles that occur very often in the real world, and so therefore we look at the relationship between the sides and angles in these special right triangles, and we're going to come up with shortcuts today to understand how the sides relate in a triangle that might have a 30, 60, 90 relationship, where the three angles in the triangle, one measures 30, one measures 60, one measures 90. The other special right being a 45, 45, 90. And we're going to have the expectation that you can recognize these types of triangles and find the sides without having to use trigonometry. We can do them using the shortcuts we're going to discover today. So let's go ahead and look at our first triangle and the shortcuts that we can create. You notice here we have a right triangle that has a 90-degree angle and two 45-degree angles. That's our special 45, 45, 90 right triangle. And I've gone ahead and labeled one of the sides 1. It doesn't matter what you label the side length as, because we're looking for the relationship from one side to the other. I've simply chosen 1 because it's the easiest number to work with. If you remember back to geometry, in geometry, in the study of isosceles triangles, we discovered that if two angles are the same in a triangle, then their opposite sides are also the same. So if we know one leg is 1, the other leg has to be 1. In our standard triangle here, if we want to find the third side, Pythagorean's theorem is the easiest way to find a missing side in a right triangle. So that leads us to x squared equals 2, which means x is equal to the square root of 2. So our third side in our triangle would be equal to the square root of 2. Now, because of similarities and proportional growth that we know about in similar triangles, this relationship that we've discovered here will hold true in every 45, 45, 90 right triangle. Our two legs will always be the same. Our third side, our hypotenuse, is always going to be equal to the leg times the square root of 2. This standard triangle we have here, you'll want to make sure you have in your notes, as we'll reference this a lot throughout the rest of the day. Our next special right triangle is the 30, 60, 90 triangle. And again, you'll note I labeled the side opposite the 30 as 1. In order to make life easy, we picked the shortest side and labeled it as 1. Now, in order to find the other sides in our right triangle, it's not quite as easy with the 30, 60, 90. We're going to have to do a little bit of trigonometry to figure out our side. To start with, we'll call the hypotenuse x, which means using my 30-degree angle, I have the opposite and the hypotenuse, so I'm going to use sine, which is sine of 30 is equal to 1 over x, which means x is equal to 1 divided by the sine of 30. And when you punch that in your calculator, you'll find that x is 2. So we look at our relationship here. Our short side is 1. Our hypotenuse is 2. That relationship will be true in every 30, 60, 90 right triangle. The shortest side will always be half the hypotenuse. In order to find our middle side, we'll use Pythagorean's theorem. Subtract 1. So y is going to be equal to the square root of 3. This is the relationship that is true in every 30, 60, 90 triangle. You will recognize that the shortest side is always opposite the 30. So you go from your 30-degree angle to the opposite side, that will always be the shortest side. The longest side will always be opposite the right angle, and that will always be double the shortest side. The middle side is always going to be the shortest side times the square root of 3. So let's look at applying this so where we can get to using our shortcuts to solve these without having to do a whole lot of work. We're going to look at two examples of 30, 60, 90 and 45, 45, 90. One is going to be very simple, one's going to be slightly more complex. Most of the issues you're going to run into with these problems will be issues with radicals. So if you look at our first example on the left, our 30, 60, 90 triangle, I have given you the side opposite the 30. That's the shortest side of the triangle. From there, we can complete this problem in a matter of seconds by recognizing the hypotenuse is always double the shortest side, and the middle side is always the shortest side times the square root of 3. So the hypotenuse ends up being 12, the short side is 6 times the square root of 3, and that becomes about a 10-second problem. Where these will become a little bit more difficult is you're going to have to be able to work with some radicals, and that's expected previous knowledge that you understand how to work with radicals. When you look at the 45, 45, 90 triangle over here, I've given you the hypotenuse, and it does not have a square root of 2 in it. And it should make sense that we went from our short side to our hypotenuse by multiplying by the square root of 2. Well, that should follow then that if we're going backward, and I want to find this short side, I'm going to have to divide by the square root of 2. And this is where we have to use a little bit of our radical knowledge, and we rationalize our fraction, never leaving a square root in the bottom, which becomes 8 radical 2 over 2, and that fraction reduces to 4 radical 2. So therefore, both sides are 4 times the square root of 2, and the hypotenuse is 8. I will help you individually with some of your radical issues you may come across, but this is the basics of how to find the missing sides in a special right triangle.